Hello viewers. In my first lecture on chemical kinetics, I introduced you to the subject. Let us recall what we studied there. We defined chemical kinetics and how thermodynamics is not able to give us idea about rates of chemical reactions. It falls in the realm of chemical kinetics. I told you what is meant by rate of a chemical reaction, what are the factors that decide the rates of chemical reactions, and finally we looked at the rate law, an equation that relates the rate of reaction with the concentration of the reactants. In this lecture, I will discuss about classification of reactions in terms of order of reaction, molecularity, and then we look at the integrated forms of rate law, in which we will look at first, second and zero order reactions, and then towards the end I will summarize what we have studied today. Let me start with classification of reactions. There are two ways in which reactions can be classified. The first way is in terms of order of reaction. This word order is actually borrowed from mathematics, where the differential equations are classified as first order, second order, third order, etc. Since our rate laws are differential equations, we can safely use the terminology here to classify the reactions in terms of order, that is first order, second order, third order reactions. But here we can also have what are called zero order and fractional order reactions. The other way is in terms of molecularity. We have unimolecular, bimolecular and termolecular reactions. What do you mean by order of reaction? Order of reaction is defined as the sum of the powers to which the concentration terms are raised in the differential form of the rate law. It is denoted by the symbol N. Let us first look at first order reactions. A giving you product, one reactant giving you product. The rate of reaction can be written as R is equal to minus dA by dt is equal to K into concentration of A. This is what we have seen in my earlier lecture, how to put the rate law. Now this tells us that the concentration term is raised to 1, and by definition of order of reaction in this case turns out to be 1. Let us look at the examples. Decomposition of diazonium chloride. You can see here, and we can monitor the reaction by measuring the volume of nitrogen evolved. The rate is found to depend on the concentration of the reactant, that is diazonium chloride, and you can see the power to which the concentration term is raised is 1. Therefore, this is a first order reaction. Let us look at the second order reactions. A plus B giving you products, or the other possibility is 2A giving you products. Rate of reaction R is equal to K into concentration of A into concentration of B, and the other possibility is rate of reaction is equal to K into A raised to power 2. Therefore, order of reaction in both the cases works out to be 2. Now, example 2HI giving you H2 plus I2, and rate is given by K, that is the rate constant, into concentration of HI raised to 2. Order of reaction therefore is 2 in this case. Similar to this, we can write equations for third order reactions, but we can repeat order of reaction can be 0 as well as fractional, as we shall see later. However, order higher than 3 is not possible. Even in the case of third order reactions, there are not many examples, and most of them involve 2 molecules of nitric oxide. Now, in general, we can write A moles of A plus B moles of B plus C moles of C plus D moles of D giving you products. the rate R will be equal to K into A raised to A, B raised to B, C raised to C, etc. So that the order of reaction N will be the sum of the powers to which the concentration terms are raised, that is A plus B plus C, etc. The term molecularity is also used. Molecularity is defined as the number of molecules taking part in the reaction. A giving you products, there is one molecule, therefore the reaction is unimolecular reaction. You can have two possibilities, 2A giving you products or A plus B giving you products. In such a case, the reaction becomes a bimolecular reaction. The above definition holds good only for what are called elementary reactions. Elementary reactions are those which take place in a single step, but we know that most of the reactions take place in more than one step, and molecularity in such a case has to be defined as the number of molecules taking part in each step leading to a reaction. That is, molecularity has to be assigned to each step in the sequence of steps. There is nothing like molecularity of the overall reaction. Here we can recall order of reaction has to be experimentally determined, and we get overall order of reaction, that is how rate of reaction depends on concentration terms. Molecularity can be 1, 2 or 3, but can never be 0 or fractional, unlike order of reaction which can be 1, 2, 3, 0 and fractional as well. So, we mentioned that most of the reactions take place in a number of steps. Such reactions are called complex reactions. In such cases, it is found that the slowest step decides the overall rate of reaction, and that is why that step is called the rate determining step. We can use the bottleneck principle to explain that. Strength of a chain cannot exceed the strength of the weakest link in a chain. Mechanism of a reaction, the sequence of steps, elementary steps that ultimately lead to the product formation, is called the reaction mechanism. Take this example, a simple example, 2NO plus O2 gives you 2NO2, but it takes place in two steps. The elementary step 1, in which you have NO plus NO giving you N2O2. In the second step, you will get the product where N2O2 plus O2 gives you 2NO2, so that the overall reaction remains the same. 2NO plus O2 gives you 2NO2. So, we have two types of rate laws. In fact, differential rate law we have seen. It tells us how the rate of a reaction depends on concentration as seen earlier, but more important and useful is the integrated form of rate laws. It shows how the concentration of the species in the reaction depends on time. What are the usefulness of our rate laws? Rate laws have three main applications. Once we know the rate law and evaluate the rate constant, we can use them to predict the rate of reaction for any given composition of the reaction mixture. And also, we can use a rate law to predict the concentrations of reactants and products at any time after the start of the reaction. The third application is a rate law is a guide to the mechanism of the reaction. Any proposed mechanism must be consistent with the observed rate law, but we know that for a given reaction there can be more than one mechanisms, and they can fit very well with the experimentally determined rate law. To decide which one is the most probable mechanism, we have to gather evidences. Integrated rate law expression. We can recall the law of mass action. Rate of reaction is proportional to the product of the concentration of the reacting substances raised to a simple power. Consider a simple reaction again to start with, A giving you products. Rate R is equal to minus dC by dt proportional to C. We introduce the rate constant, and then we get the rate constant and the integrated form of it, C is equal to C0 exponential minus kT. This is what we have seen. the concentration profile that Wilhelmy got in his first experiments on chemical kinetics. Now, the same thing can be looked at individually. For a first order reaction, what will be the integrated form of rate expression? Consider a first order reaction, A giving you products, reaction R is equal to minus dA by dt is equal to K into A. If we put the concentration of A to be A after a time t, A minus x, where x is the amount of A that has reacted in time t, then we can write the differential equation minus dA A minus x by dt is equal to K into A minus x, and a sequence of steps, and then we rearrange it to get in the form which can be easily integrated, and integration will ultimately lead to first evaluation of the integration constant, and then we get the equation, final equation, integrated form of the equation K is equal to 2.303 by T into log A upon A minus x. The unit works out to be time inverse. Generally we use minute inverse, and this is the first order rate expression. Let us look at the characteristics of first order rate expression. The expression is K is equal to 2.303 by T into log A upon A minus x. The unit of K is time inverse, and K is found to be independent of units used for concentration. If we rearrange the equation and plot log A minus x versus T so that we get a linear expression, you can see clearly here we get a linear plot log A minus x versus T, which can be extrapolated to get log A. From the slope we can evaluate the rate constant K. From the slope we are calculating the rate constant K. Another important characteristic of the reactions, chemical reactions, is half-life. What is half-life? We define half-life like this. It is the time required for the concentration of the reactant to decrease to half of its initial value. It is denoted as T half. So, let us take the integrated rate law expression of first order reaction and put T is equal to T half when A becomes A by 2, and in such a case we get the value of K to be equal to 2.3 upon T half log 2. On rearranging we get T half to be equal to 0.693 upon K, and K is 0.693 upon T half. We also define what is called relaxation time, which is denoted by tau, that is equal to 1 upon K. So, half-life of first order reaction is independent of initial concentration of the reactant. That is obvious from the equation that we have. Concentration term A does not appear anywhere in the equation. We have to remember this, it is important. We can look at the graph here. If we plot the pressure versus time and look at how pressure decreases with time, when it becomes half, it is half-life, first half-life, and it becomes half from this value, the second half-life, and successively we can find out for every duration of half-life the pressure becomes half and half and half. By that way the reaction never goes to completion, it becomes half of what is there in the previous step. Examples of first order reaction: hydrolysis of methyl acetate in presence of dilute HCl, often repeated example, we are familiar with it. In this case, if you look at stoichiometry 1, 1, 1, 1, the reaction can be followed by titrating aliquots of reaction mixture at regular intervals against standard sodium hydroxide using phenolphthalein as the indicator. And in this case, we take water in excess and we find out how much of acetic acid is formed during the course of reaction after definite time interval. So, the rate, if you write R is equal to K into concentration of ester into concentration of water. Since water is taken in large excess, its concentration almost remains same during the course of the reaction. So, we can consider that as constant. so that we have the rate law which becomes R is equal to K prime into concentration of the ester, so that the order of reaction is 1. The reaction is a bimolecular reaction expected to follow second order kinetics, but the conditions are such that it follows first order kinetics. Such reactions are called pseudo first order reactions or pseudo unimolecular reactions. Let us now look at the second order reactions, 2A giving products or A plus B giving products. In the second case, we are taking concentration of A and B same, so that we get a common equation as the integrated law expression. K is equal to 1 upon T x upon A into A minus x. And you can see here the unit concentration inverse time inverse. What are the characteristics of second order reactions? First is unit of K itself, which is different from that of the first order reaction. A plot of 1 upon A minus x versus T is a straight line. This we get after rearranging the equation for rate constant. You can clearly see here 1 upon A minus x versus T is linear. From the intercept you can get 1 upon A and the slope gives you the rate constant. We can work out the half-life. Half-life is equal to 1 upon Ka. Again different, because half-life in this case is inversely proportional to the concentration of the reactant. So, increasing the initial concentration will decrease the time taken to reach 50% conversion, whereas in the case of first order reaction it is independent. By increasing the concentration you cannot get your product faster. Second order reaction, A plus B giving you products with A unequal to B. If we start with different concentration of AB, we get an expression which is slightly different. K is equal to 2.303 upon T into A minus B log B into A minus x divided by A into B minus x, and the concentration inverse time inverse as the unit. Examples of second order reactions, again a common example, saponification of ethyl acetate, and you have sodium hydroxide. Here we can use a conductometric method for following the reaction. The reaction can be followed, as I told you, by measuring the conductance of the reaction mixture at various time intervals, and data obtained fits in very well with the rate expression for the second order kinetics. The reaction between potassium persulfate and potassium iodide in aqueous medium. Another example, liberated iodine can be titrated so as to follow the reaction. The third example, reaction between ethyl bromide and potassium iodide in 99% methanol. And there are other reactions which follow second order kinetics, 2NO-Br giving you 2NO plus Br2 and 2NO2 giving you 2NO plus O2. Zero order reactions, very interesting. The rate is independent of concentration of the reactant. You start the reaction, the rate remains same throughout the reaction. Rate is equal to constant. We can write the expression minus dA minus x divided by dt is equal to k. So, that minus dx by dt is equal to k, and we can finally get the integrated form of the rate law. K is equal to x upon t, concentration into time inverse, and half-life we can calculate. Half-life T half is equal to A upon 2k. Again different. From first order, second order to zero order reaction, we have expression for T half much different, and we get a clue here. It is possible for us to identify which order that the given reaction follows by looking at the half-life. In this particular case, if you plot x versus t, you get a linear plot from which k can be evaluated. Examples of zero order reactions. There are not many cases of zero order reactions, and whatever reactions that we come across take place on surfaces. These are heterogeneous reactions in fact. A very good example is this: ammonia decomposing on a surface of platinum at high temperature. The rate is independent of concentration of ammonia. rate is equal to rate constant. And the second is again oxide of nitrogen on hot platinum wire. And the third example is the decomposition of HI on a gold surface. How do you explain this? When the gaseous reactants are in contact with the surface gets saturated with the reactant, so that the concentration of the reactant available on the surface where the reaction takes place is constant. Therefore, the rate of reaction becomes independent of the concentration or the pressure of the reactant in the gas phase. That is how we get constancy in the rate of reaction. At the site of reaction, concentration remains constant, and therefore rate of reaction remains constant. To summarize reaction and the kinetic equations that we get, here it is: the order of reaction, the rate law, integrated form of rate law, and the half-life of the reaction. You can see the difference in the integrated form of rate law and their units, and you can see half-life of the three types differ. This will help us in experimentally obtain data to be used in order to find out exactly what is the order of the reaction that is under investigation. So far, we have seen examples of first order, second order, and zero order reactions. Now, is there any relation between order and stoichiometry? Look at this example. It tells us it is not necessary. Now, if you look at the reaction here, 2N2O5 giving you 4NO2 plus O2, it appears to be a second order reaction, but follows first order kinetics. See the other example, H2O2 plus 2H plus 2I minus giving you 2H2O plus I2 appears to be a fifth order reaction. 1 plus 2 plus 2, we are adding the stoichiometric coefficients, but it follows second order kinetics. It is found to be first order both with respect to H2O2 and I minus. Therefore, we have to be very cautious in talking about order of reaction. Order of reaction cannot be predicted from the stoichiometric equation. Order of reaction has to be established only by experiment. Let me summarize what we have discussed in this topic of chemical kinetics. I introduced you to the topic of chemical kinetics in my first lecture, importance of rate of reaction to industry and to the laboratory chemists. Factors affecting rate of reaction we have discussed, and then we try to establish a relation between the rate of reaction and concentration, which is called the rate law. Now, it is possible to classify the reactions on the basis of two terms. One, order of reaction. This term order is borrowed from mathematics. Rate equations are differential equations, and therefore we can classify the reactions in the terms of order: first order, second order, third order reactions. The other term that we use is molecularity, on the basis of which we have unimolecular, bimolecular, termomolecular reactions. And the differential rate laws are less useful than the integrated forms of rate law, and therefore the integrated rate expressions for the first order, second order, and zero order reactions have been established. You may see why there is no third order reaction equation or rate law, because these reactions are very rare, and in most of the cases you will find nitric oxide as the participant. So, we will not bother much about third order rate reaction. And in my next lecture, I will discuss about methods that are used in following rates of chemical reactions, as well as methods that can be employed to establish the order of reactions. Thank you.